same grade. The diffraction pattern can be changed a bit. So when the pattern change a bit, it can take effect on the match value. So this value can be increased, this can be decreased. So the answer can be changed from the first one to the second one, or to the third one. This is the reason of this noise. For two-dimension EBSD, there is a software that the post-processing software that can correct this noise, but usually we don't have that software. And here is a tetragonal structure orientation of this T orientation. We have two oxygen. The red oxygen is located at the short side of the tetragonal structure. So here the short side, and here and here. So if this is cubic perovskite instead of tetragonal, this means this side equal to this side and this side. These three orientations are the same orientation. So for cubic structure, we will not find this problem in cubic structure. And yes, this is my future work. I plan to do EBSD at the interface between the electrolyte layer and strontium titanate active layer of SOS EC cell. That is conclusion. So EBSD technique you can use to measure orientation of crystal, and also can do phase identification and investigate grain size, shape, and barrier. And for my study, I found these three important problems of doing EBSD of SOS. The charging problem that for some material that we can solve by coding, and FIB damage. We may need to investigate FIB damage before EBSD if the pattern is not good, and slow symmetric problem for low symmetric crystal structure as tetragonal. Take it out.
Do we have some questions?
Good.
Oh, yes.
James Wilson, Northwestern. I just had two questions. One was looking at this FIB damage. Can you go back to that plot you had? I just wasn't sure what the vertical axis is. So you said the higher number is better, but what are you measuring? What is band contrast? So that's, you're saying about the pattern that you're actually reading?
Yeah.
You're getting higher quality patterns.
Higher band contrast. Yes. Here is the contrast between them. So
Is that just an arbitrary number that's kind of...
It's a number that's, it is an arbitrary number,
Yeah.
but it's a measure of the contrast between the bands and the background of the image.
So in the Kikuchi lines, or?
Yes.
Now, my understanding of EBSD, or at least sample prep with, an ion beam, and this, I think I mentioned this at some point, was that your depth of damage is going to be a function of the beam energy, not necessarily. I mean, obviously, you're getting also a function of the current. But is it conceivable to go to lower energy to reduce the damage, or is that too much of a trade-off in the time to mill?
Yeah, I think that's an interesting point. I agree with you.
But I think
Haven't tried it.
we haven't tried it for practical purposes because each time you change the accelerating voltage, you have to make a new probe. So it's easy to change between probe currents compared to changing between accelerating voltages, because then you'll need to actually reprogram a new set of probe currents each time you change the accelerating voltage, because it changes your condenser values and
Yeah.
all the other alignment. So I think maybe we could go down to 20 or 25 kilovolts, but I think once you start to go down any further, then the ability to focus the ions and get a decent probe is more and more difficult. Maybe Dan can comment on that.
That's correct, basically, yeah. But it all depends on the type of instrument you're using.
Yes. So we're using a 1540 cross beam. I think it will be easier maybe with an emission voltage.
Absolutely.
But Laurent, do you have any experience with?
Yeah, well, probably the same position will depend very much on the instruments. Not impossible, but indeed, I mean, like you said, the first step is really to get to, let's say, a beam that can be properly focused so that you can take automate the whole thing. It's not completely science fiction. Work in that direction, but it's not completely obvious. What's been published, however, is that indeed if you use a low kV, we're definitely seeing, let's say, assuming you can do 5 kV, I mean, it's been published that you really get to better patterns.
And I must say, nowadays, this low KV polishing is something really state of the art on all the FIB-SEM instruments, because for all this DM, the metal preparation stuff, it's a must. You want to have a high quality DM.
But I think maybe for EBSD, if you're switching, if you want to remove a lot of material between each slice, you have to do a coarse polish then a fine polish, which adds time to change between. So you have to shut the gun down and restart it up each time. Are there any more questions?
That was just a comment on these two probe currents or milling currents, 100 and 200 picoamps, that deviates from the straight line that you expect. Maybe it's related to the way the surface was prepared, so you actually still see the effect of how you were prepared to solve from the start. Have you tried actually doing any deep pattern on the non-mill surface? Just the answer is?
I think maybe the answer to the question is maybe we should mill deep with a high probe current and then repeat with a low probe current because there might still be some damage from mechanical polishing. So that could be one.
Yeah, just something to try.
But this was the first experiment we've done. Time for one quick question. It's not the case.
Quick comment. You said you didn't have the software to kind of get rid of those little spot errors. You might be able to just program something on your own because you have this band contrast image that basically identifies the grain, but then within that you've got all these colored pixels. If you could identify the grain, just add up what all the colors are and just take whatever the max is.
We actually have a collaboration with Oxford Instruments, so I think this is just a trivial question that we're not getting into implemented. So I think that would be our preferred solution.
Yeah.
Okay, let's thank Nath again.